When we study meteorology at the intermediate level, we're going to be expanding upon a lot of the principles from the primary level. So it's important that the students have a good understanding of those. One in particular, the one with the balloon with the popcorn in it, and the idea that the particles are closer together near the surface of the Earth and further apart up at altitude, like on a mountaintop. And the other idea is that the particles get further apart when they're heated. This gives us a basic understanding of the density of gases and why one gas is seemingly lighter than another gas. The hot air rises, for example. Now, we want to explain back to our astronomy model. We want to explain why we have seasons, why this tilt of the Earth gives us seasons. Using the astronomy model and maybe making some actual observations, we can see that in this particular situation, the southern hemisphere will have more hours of daylight and fewer hours of darkness as the Earth turns on its axis. In the 6 month later position, the northern hemisphere will have more hours of daylight. Now, how does this affect the temperature, the heating of the Earth? Well, we want to go out and do an activity to demonstrate that. 2 bowls of dirt, same kind of dirt, try and get dry dirt. Put a thermometer, same types of thermometers in each bowl of dirt, and put them both outside at the same time. Be sure and number them so they don't get confused. Every minute or every 2 minutes, have the students go out and record the temperature of each. Leave bowl number 1 in the sun for only 15 minutes, and leave bowl number 2 in the sun for 30 minutes. And see what the temperature in bowl number 2 has risen to as the sun gets to shine on it longer. You'll find that this dirt gets hotter. So we can see now, we get the idea that the people in the southern hemisphere have more heat being absorbed into the land, into the water, when it's shining on them longer. So it makes this particular part of the Earth heat up more than this particular part in January. It helps us to explain why we have seasons. And it also gets the students to understand that dirt is holding heat. And then we want to go on and talk about the rates at which dirt and water heat up. Which one do you think will heat up fastest, dirt or water? And which one will cool off quickest? Well, let's go and look at those experiments next. Somehow it's just not easy to get excited about a bowl of dirt and a bowl of water. But there's really a lesson to be learned here. As you put these two out in the sun together, you'll find that the dirt heats up quicker. And then when you take them back inside and let them cool off, you'll find that the dirt cools off quicker. The dirt doesn't hold the heat like the water does. And from this experiment, and graphing these is really good because you can see the comparison between the two. From this experiment, you can understand why we have winds, because the air over the land heats up quicker than the air over the water, and that air rises because it's lighter, so there's nothing left here. So the air that's colder, that's sitting over the water, has to rush in to take its place, and this causes the wind. And in the evening, when this land cools off, this cools off first, and this water still holds its heat. And now we have the reverse effect, with the now warmer air over the water rising and the colder air near the land moving toward the water to take its place. It's a good concept, and if you can get excited enough about it, you can make this dirt and water activity work for you. Many important principles of weather can be illustrated using a simple model like this. We have a pan of water on one side, a large rock in the middle, and another pan sitting on a hot plate, and this pan with dirt. First, we're going to illustrate the fact that hot air rises. Watch this. Whoa. We want to reinforce these ideas that when you heat up dirt, whether it's by the sun or by your hot plate, we're going to have the air over it rising, and we're using our convection mobile from the primary grades to measure it. And when we have this air rising, we're creating a low pressure area over here, and we have this high pressure area here, so we're going to have a wind going from high to low. Now we want to introduce the problem of how the surface features of the Earth affect the path of the wind. So we want to take a new look at our model. This time it's the ocean and a mountain range and the desert. And why, for example, on the west coast, do we always have deserts on the east side of the mountains? Well, we have to evaluate a lot of the things that we've learned already and put a little logical thought into it. Ideas like, is this air that's over here have a lot of water in it? And if it does, and as it rolls up the side of this mountain and pushes up higher into the sky, what will happen to that air? Will it get hotter or will it get colder? And you have to think of all the little molecules moving around back from the primary grades. And as it gets higher up in the air, there's less air pushing on it, so the molecules get further apart. They expand. And as they get further apart, they're not hitting each other as hard. They're maybe not hitting each other as often. So they're going to be cooling. There's going to be less energy transferred between them. So we have a decrease in temperature. So when the air particles are rising, its temperature is decreasing. As gases expand or get bigger, the particles get further apart, they hit each other with less frequency, and they cool. That's a very important concept to get through to your students. Now, here's the air that just came off the ocean, and it's got a lot of moisture in it. And it's coming up here and it's cooling. What do we know will happen when air with lots of moisture and it gets colder? Well, it's going to start turning some of these particles. The moisture it can hold becomes less, and these particles are going to turn to water droplets in clouds first, and then the water droplets are going to coalesce together and make raindrops of different sizes, and eventually it's going to dump a lot of rain here. So on the west side of the mountain range, we always have lots of vegetation. Now we have this cold air that's come over the top of the mountain, and it doesn't have much water in it, and it comes over this warm land and it starts to get heated again. Now it can hold a lot more moisture. So what it does, it sucks the moisture out of the ground. It takes the moisture from the plants and it makes the deserts. And this is why we have the deserts on the east side of the mountain range. Now, this is a really important concept because we want to understand that air cools when it expands, and when it compresses, it heats. The molecules come closer together and it gets hotter. And we can demonstrate this with two simple activities. One, get a can of hairspray, cheap hairspray, hold it out and spray it. And just have the student that's doing it feel what it feels like around here. Put your finger right on the sprayer as soon as it's through spraying. And it'll feel cold. It feels cold because all the gas that's compressed in here is coming out and expanding out. The particles are getting much further away and they're cooling. And it's getting cold. And anytime we release gas, you get a scuba tank and let all the air out, it's going to get real cold. Your stove, your camp stoves, when you're releasing that propane gas to cook on, the fixture and everything gets cold because the air is expanding. And on the contrary, when the air compresses over here, you can use this activity, just a regular bicycle pump, and get some kids to just go crazy with it. Pump it as hard as they can. Pass it on to another kid and pump it. And then feel this little valve stem right here where all the air was compressing. It's going to get real hot. And this illustrates that when air is compressed, it heats up. There's other questions we can ask and answer using this model. For example, why is it cooler on top of a mountain than it is down below? Think of the sunlight shining through the air. The air is transparent to the energy of the sun, and the sunlight goes right through the air. It hits the earth and heats it up. Only the air near the earth is going to be heated. So this air has the heat, whether it's over the land or the water. Now this air hits the mountain and rises. As it rises, it expands and it cools. And the person on top of the mountain is going to experience cooler air than the person down below. Another good question. Why is the climate so much different on the east coast than it is on the west coast? Well, we have a westerly wind. The wind has a tendency to blow from west to east across the United States. Now, the people in the east have had winds that have been blowing over dirt, over land. And remember from our experiment that land heats up quicker and gets hotter, and in the summertime that wind is going to be real hot. And in the wintertime the land cools off quicker and gets colder than water, and that wind is going to be much colder and cause extremes of seasons here, hot summers and cold winters. Whereas the people on the west coast are getting wind that's traveled over the water. And we know that water stays pretty moderate in between hot and cold. It doesn't heat up too fast and it doesn't cool down too fast. And the winds that hit them are not going to be in the extremes, and we're going to have a much more moderate climate here on the west coast. Another concept you should cover using this model is what we call the water cycle. Now the water cycle involves the evaporation of water from the ocean into the air, and then the condensation of this same water over the land when it rains. The water vapor cools and condenses, rains on the land, and then the water finds its way back to the sea through the lakes and rivers and even through the water table. And it's a continuous cycle. And one idea you might ask your students is, think of the next glass of water they drink, and think about how many times that water's gone through this cycle. Now we've come to my favorite activity, and that's making a hot air balloon. And I took my plans from Science and Children magazine, November-December issue 1983. And you can look up the plans for yourself. What we've got is a pattern made out of 2 pieces of newspaper, and you want to have more than one pattern for your students to use. Using this pattern, we make 6 panels for the balloon, and we glue all the panels together. And be sure and use glue sticks and not the glue that comes out of the bottle, and telephone wire on the end. Now when you're heating the balloon up, you can use either a hibachi or a camp stove, and you don't need to make any complex chimney apparatus. Just cut out the bottom of a juice can and set it over the top. Now, in a very brief period of time, we're going to look at a workshop where a bunch of teachers did this. They made a hot air balloon and we flew it, and you're really going to enjoy this. Now, wouldn't you like to do that? Have a hot air balloon derby in your school. Have your kids make them. Launch them during the lunch hour. See whose balloon goes the highest, whose balloon goes the furthest. Give awards for the most colorful balloons. You might even want to have 2 or 3 stoves going at once. Be sure and have some good warm mitts so you don't burn your fingers. Now, you want to have recovery teams to get the balloons. And another thing you can do is measure the height of the balloon. How high does it go? And we got to get back to these little things, the quadrants. The ones that we made for the astronomy lesson. These have a lot of valuable other uses. To measure the height of the balloon, have the students pace off from the launch site, maybe about 100 feet in either direction. As the balloon goes up, they measure it and sight it and measure the highest angle it reaches. And then back in the classroom, we plot these distances and scale them down on a piece of paper. Say 1 inch equals 10 feet. So we draw a line that's 10 inches long. That's our 100 feet. Then we inscribe the angle we measured using a protractor. Say the measurement came out to be 50 degrees. After that, we draw a straight line up on the other end, where the balloon went up. We then measure that line with our ruler. If it measures out at 12 inches, then we know from our observations that the balloon went up 120 feet. You can see that these balloon activities are great, and not only is there a lot of fun in it, and it gets kids turned on to science, but there's a lot of practical value. It shows how inventions were made, how technology has been utilized, scientific ideas of hot air rising to take man aloft. And you may even want to have the students invent their own balloon and let them make their own pattern in their own shapes and see whose balloon goes the highest. Now, don't even ask me what this has to do with weather, but it's such an interesting activity I had to show you. A way to do a little more with your balloon. Ask your students what they think will happen if you stick this knitting needle into it. If you do it really carefully and just right, and bunch up a little bit of the material down here at the bottom and put it in right near the knot, then you can insert this knitting needle right into the balloon and maybe get a nice tight seal so the air doesn't leak, and then keep pushing it through. All the way through, oops, a little bit of air leaking out here, to the other end, and then you can push it through right through the top too, and if you put your fingers around it when it comes through, you can make nice seal there. Oop. Let's try and seal this air off. And we now have a speared balloon. There's many factors that affect our weather. One of them is air pressure. And to review what air pressure is, that's the force of the air pushing down upon us. The fact that we're in the bottom of a column of 50 miles of air over our head, and that air has weight, and it exerts quite a bit of force. But because it's acting from all directions on us, we don't really see the effects unless we can isolate it. Now let's take a look at some activities to do just that, so your students can understand more about air pressure. First one you've probably done yourself. That's filling a glass with water, carefully taking it out and putting a card over the top and flipping it upside down. Well, I'm going to try one step further, and this one requires a few trials and errors, so be sure and do it over your tank. Put a piece of wet cotton over the top instead and press it down along the sides of the glass so it kind of gets a little bit of adherence. And then you just got to go for it. Put your hand over it, flip it upside down, and you got it. And if you look real closely at the inside of the cotton, you're going to see this concave shape as the air is pushing on it, trying to get in. It's much more dramatic than a playing card. Once again, be careful because it may take 3 or 4 tries to get this to happen. Another one I just discovered recently was an empty soda can, and if your glass fits it just right, you can flip it upside down. See if I can do this one. Flip it upside down and have the air pressure be strong enough to hold this whole soda can up against this glass, like that. Ooh-wee, look at that. Okay, we're on a roll here. Now, we want to trick our students, and we want to use the same principle of the air pushing down. So, get a regular plastic cup, and before you bring it into class, get a hot nail with a pair of pliers, bore a hole in the side. Make sure it's marked with like an O on the word here, so you can always cover it with your finger. You can always find it just by looking at the word. And you're talking about air pressure, and your students have probably done this before. Put your finger over the hole, hold the cup up and say, why isn't the water running out? Get them to come up to the answer with the air pressure pushing on this water but not pushing on this water. And it's keeping the water from falling out because there's all this air pushing it and driving it up. And in fact, you could hold a glass of water that's 33 feet tall up, and the air would hold that much water up. That's the limit. 33 feet of water is the same weight as the 50 miles of air. And then you get a student from your class to come up, and you trick them, and you say, okay, reinforcement time, I just want to see you do this activity. So they come up and they grab it, and they don't know about the little hole, and before you know it, you just say, hey, what's happening here? What's going on? Why can't you make it happen the way it's supposed to? The water keeps running out. And eventually, and it's a good way to learn. Kids really can learn a lot more from an activity like this where they're tricked than where it's just shown to them. Eventually they may go and try another experiment and say, the only possible conclusion is that air must be getting in that cup. There must be a little hole in it. And sure enough, when we try this experiment, we find that it also doubles as a dribble cup too. And now let's examine the final experiment, the famous crush the can experiment. The way to get rid of all those ditto cans, the empty ones that are piling up in your stockroom. Get your hot plate, get your ditto fluid can, and put about a ½ inch of water in it and heat it up to boiling. And while the water is boiling, ask the students what they think is happening or what they think is going to happen when the water boils and it turns to steam. And is there any air in this can? Is the air being driven out by the water? And is the can now filling with water vapor? Those are the kind of questions you want to get and the answers you want to get. And then as you start to see the steam come out, you know that the can is filled with water vapor only and very little air. And make sure that your cap still has the seal in it. Make sure you have a good pair of pliers around so you can tighten the cap down, and a good hot pad so you don't burn your fingers. We see the steam coming out, so we're going to quickly remove the can off the burner and then cap it. Don't cap it while it's on the burner. And get it capped real tight with your fingers first, and then using the pliers, tighten it down so that no air can get in. Now, what is going to happen? All these water molecules in here that are now in gas form are going to cool. And when they cool, they're going to condense. So we're talking about air pressure, we're talking about evaporation, and we're talking about condensation. As they condense and turn to tiny droplets of water, and it takes a lot of gas particles, a lot of gas molecules to come together to make one drop of water. The little drops of water hit the sides and run down the sides. And there's now nothing inside this can. It's a vacuum, a partial vacuum. And all the air outside is trying to get in. It's saying, hey, there's nothing in there, pushing back against the wall to equalize the wall. So I'm going to try and get in there. It's going to try and find its way in. Now you can do it slow and let it cool in the classroom, and you can see it starting to bow in. Or you can do it real quickly by dousing it in a tank of water. And as that cools the walls down, you'll see the can go through some very drastic changes almost immediately. And it always amazes the kids when they see this activity. And you really get to understand the force of the air. There's really an incredible amount of force of the air, all that 50 miles of air that's pushing down upon us. Now let's make a smooth transition from air pressure to temperature and humidity. Temperature and humidity are also very important factors which influence our weather. Now let's start with this imaginary experiment. Imagine this container is filled with water, and we're going to represent our water molecules, H2O, as 2 hydrogen atoms bonded to 1 oxygen atom, and they sit kind of like this, like Donald and Mickey Mouse here. All these water molecules moving around in here. Now if one of them is moving upward, and at the same time another one's moving faster in the upward direction and hits it, it's going to give some energy into it, just like billiard balls on a pool table. And this one particular particle will gain enough speed, enough energy, so if you could measure the temperature of just that one little molecule, it would be at least 100 degrees C. It's got that much energy in it. So it goes flying out, and that little particle is evaporated. Now some of them go flying out at different temperatures. The temperature of the whole liquid on the average is what you're measuring. You're not measuring the temperature of individual particles. So this little particle goes flying out into the air, and it stays as an H2O. These don't break apart. It's in the space between the air molecules flying around. Now, the warmer the air, the bigger the space, so the more particles that can go in there. But the other thing we have to consider is the pressure aspect of it. There's this pressure of the air pushing down on the water, and it's fighting these particles that are trying to fly out. So there's a certain pressure that's required of this water particle before it'll go up into the air. Now, if you've got this idea through to your students, ask them this question. What do you think would happen to water if you went up on a mountaintop where the air pressure is less, pushing down on it? It's not pushing as hard on these little particles. Will the water boil sooner? Will it boil at a lower temperature? Will it boil at the same temperature, or will it boil at a higher temperature? Good logical question, and now we can start to understand why when you're camping in the mountains you have to boil an egg for a few minutes longer. Now let's examine the reverse effect, and that's what happens inside of a pressure cooker. Remember, we've sealed the top off. We're heating the water up to boiling. Some of the water particles go up into the space inside the pressure cooker. More and more particles go up. We're compressing this particular gas that's in there. The pressure of that gas is now pressing down with more force on top of the water. So fewer particles can go flying into space unless they get more heat energy, more speed. So we have to heat it up even more. So we're changing the boiling point of the water. We're making it hotter now. And vegetables and whatever you cook in pressure cookers always cook sooner. Now, what happens to these little particles when they do go flying up into space? They're out here floating around as vapor particles. And how do they turn to rain? Well, to get rain to happen, you need to have one other item, and that's some type of nuclei, a piece of dust or something floating around in space that the water particles can latch onto. Let's say we have a piece of dust here, nice piece of dust, floating around in space. Now as this dust floats around, it rubs into things like water molecules, and it gets charged up. It gets electricity rubbed onto it or rubbed off of it. Now let's say that this little piece of dust gets charged up with a plus charge. So here's a piece of dust with a plus electric charge floating around in space. Here's our water molecule. Our water molecule is H2, that's 2 hydrogens and 1 oxygen. And these have electric charges on them too. The oxygens over here are minus and the hydrogens are plus. So when this little minus from the oxygen gets near the plus from the dust particle, it's going to latch onto it. And if it's not going around too fast, flying around too fast, it'll stick. If it's flying around too fast, it's still too hot, and it won't. So it'll just keep going, and we won't have much moisture condensing. But if it's cooled down, slowed down, it'll stick to the dust particle. And more of these will stick to this dust particle. And eventually, they'll coalesce and come together and form a drop. And as the drop grows, it forms a raindrop and eventually falls to Earth. But it'll start out as a cloud. Now, how do we go about measuring the amount of the water in the air? And now we're going into this transition into humidity. At the primary level, the student was introduced to the concept of humidity using the tomato juice can with the cold water in it, where he or she measured the temperature of the water when the first condensation appeared. This was really a measurement of the dew point. That's the temperature of the air when the water condenses out, when the water particles come out. It is related very closely to humidity. And when we read in the paper, the humidity is 80%. What does that really mean? Well, air at a certain temperature can hold a certain amount of water, and the warmer the air, of course, the more water it can hold. Now, if the air is completely saturated with water, holding all the little water particles it can, we call that 100% humidity. That's maxed out. If it doesn't hold as much, say it holds 80% of its total possible, then that's what 80% relative humidity means. It's relative to the total amount that it can hold. Now, how do we measure this particular characteristic of an air mass, the relative humidity of it? How humid is the air? The easiest way I find, there's lots of ways. There's things that use hair hygrometers, and there's things that spin around. But I like to use two thermometers, and this works, and it's really an interesting experiment. Put a piece of shoelace that is kind of hollow inside, hanging around the bulb of one, dip it in some water, get it wet, and then set it out and fan air across both of them. Make sure that they're both the same type of thermometer. As the water evaporates from this piece of shoelace, it's going to cool. And when it cools, it's going to make this thermometer read lower. Now, if there's not a lot of water in the air, then a lot more water is going to evaporate, and it's going to cool it down even more. If the water is already saturated, it's got 100%, then the water is not going to want to evaporate from here at all, and the temperature is going to stay pretty much the same as the temperature of this thermometer. Now, you have to use tables, and it's a good activity in reading tables and going across, because it's kind of a fun table to read, the relative humidity table. And you can find them in encyclopedias and in science textbooks. Make sure that the humidity table you're using is in the temperature scale that you're using. In other words, they have them for degrees Fahrenheit and degrees C, and depending on the thermometers that you use. It may even be good to try them both. So you can measure the relative humidity and record it on a daily basis. Keep weather charts and have your students do little mini experiments where they're finding the amount of rainfall in a 1-month period, or keeping track of the temperature on a daily basis, and then reporting back to the class. And now you're incorporating the reading, the writing, and the math skills too. And then look back at the earth sciences as a whole and see how you can really get a general understanding of our natural world by studying them. Now, with all this information, this vast amount of information, where do we go from here? Well, first you should confer with your colleagues and decide who's going to teach which topic, so we don't have any redundancies. Who's going to take the astronomy? Who's going to teach the meteorology? And then you also have to remember that there's two other main areas that need to be covered. There's the physical sciences and the life sciences. And at your grade level, there's probably particular topics that you should cover. And once again, these have lots of fun activities that we can do to illustrate some of the principles. You also need a good solid textbook, and there's a lot of new books out. And if you're like most schools, you haven't purchased books in a while, check with your district office and see how close the new textbook adoption is coming up. And then take a look at the 5 or so good book series and pick a book that you like the best. But it's not just books and activities that make a successful science course. It's how interested you are in the subject. The bottom line is your enthusiasm, because it'll be through your eyes that the students will see what science is all about.